Okay, let's see, folks. So let's resume with the last talk of the day, given by Parinya Chalermsook from Sheffield. Thank you.
Thank you. Yeah, so I'm going to talk about like several connections between extremal combinatorics and theoretical computer science that arise in my work. Some of you may have heard this talk already because it's always my thing to, whenever I move to a new country, I will give the same talk for the whole year. So like introductory talk. So if you invite me next year, it will be a different talk. So, okay, anyway, so it will be quite high level. So there's no proof at the end of the day. So it's perfect, I guess. All right. Okay, thank you. Okay, so yeah, so this is the outline, and I will start with so basically this is the theme of the talk. So roughly there are three main players here: algorithms, combinatorics, and structures. So let me try to go through each of them. So here is like computational problems that probably you all know. The first one is clique, and omega t is the clique number. And the second one is the stable set or independent set. Alpha t is the size of maximum independent set in the graph. And the last one is chromatic number. So, and in computer science, we know that these problems are NP hard, and not just that, it's hard from every perspective that you can think about. Let me say a few words about what I mean. So let's look at one problem, the stable set. This one, of course, is NP hard, but as I said, it's not just that. So let's look at regimes that deal with NP hardness, approximation algorithms. So we are interested in like approximate solution, and in this case, we know that it's NP hard to get like non-trivial approximation. Like you cannot find a clique of size, independent set of size polylog, even when you know that independent set of size n to the 0.99 exists. And parameterization is W1 hard, so you cannot find a good parameterized algorithm. If you, let's say you want to get a sub-exponential time algorithm, this is also impossible, assuming exponential time hypothesis or ETH. And even if you combine the two regimes together, let's say I want exponential time approximation, you cannot do any non-trivial results. So that's one of my results in the early years. And let's say you want to combine parameterization and approximation, you also cannot do anything non-trivial. So basically, the problem in its generality cannot be addressed algorithmically like so much. Okay, so that's so what do people look at in terms of stable sets or independent sets? So that brings in the second player, the structures. So we look at the graphs that have some structures, for instance, planar graphs or bounded-tree graphs, minor-free graphs, or intersection graphs of objects. So these are examples. So all of these are well-known. Intersection graphs are less well-known. So let me say a few words. So let's say these are rectangles. And intersection graphs of rectangles is just whenever the rectangles correspond to vertices, and whenever they intersect, you draw an edge. So that's called rectangle graph or intersection graph of rectangles. Okay, so when you want to analyze an algorithm, so now we are interested in algorithmic problems in structure graphs. So the question can be phrased in an abstract way like this. So I'm given an input, let's say a graph with some property, let's say a planar graph. Then I want to say that my algorithm satisfies some property, like it costs the way I want to prove. Yeah. So this is quite an abstract question, but this is what we do in algorithms analysis. And okay, now that was the goal for algorithms on structure instances. Let me shift to the third player, extremal combinatorics. Yeah. So, and I will try to connect them together. Okay, so what is extremal combinatoric? In general, there are many ways to define it, but one way is that you are given some combinatorial object, and let's say we are interested in the combinatorial object has some property, and we are interested in proving some bound about some quantity. So fg less than or equal to b. Yeah. So the graph has property p, and I want to analyze some function f. That's the generic extremal question. For instance, one of the oldest extremal questions is this one. Mantel and Turan prove that any triangle-free graph has at most n square over 4 edges. So we get some advantage. Usually the graph can have up to n choose 2. But if your graph doesn't have triangle, it goes down to n square over 4. So that's the factor 2 advantage. And so here, the function f I'm interested in is the number of edges. And the property I'm interested in is being triangle free. Okay, so this is the structure, and this is the bound. Okay, and this one is similar. So this one, the proof can be taught to an undergrad, but it's a bit harder. So let's say any graph without a cycle of length 4 has at most n to the 1.5 edges. Okay, so I always taught this proof in my class. All right, so okay, so all the notations are clear. So if you notice, this looks very similar. And so the first one, my input has some property, and I want to analyze an algorithm. The second one, my input also has some property, some structure, and I want to analyze some bound, some concrete extremal bound. The second one is purely mathematical. The first one, I need to define out an algorithm. So it depends on the algorithm. Okay. So there are many such results that appear in the literature of algorithms. And some of them are somewhat hidden. So they are not highlighted. For instance, the old result of Hart and Chalermsook in the area of data structure, they prove the connection between extremal problems that we call forbidden matrix and a data structure that is called path compression. So they prove that this is equivalent in the sense that if you analyze the bound for one thing, it implies the other, and vice versa. So equivalent up to, I think, a constant factor. Okay, so that's the first one. And this thing is more well-known, is Davenport-Chinsel and the complexity of the word envelope. So I'm not going to define any of them except the one that concerns me. So the third one, for instance, I don't know who this belongs to. It's like there is something called Adler-Gerd problems, and there is the notion of spaners. So they have like correspondence in this way too. If you prove one thing, it implies that some algorithm give you an optimal spanner. Okay. Or if you prove lower bound, the upper bound for spanner, it implies the solution to Gerd problems. Okay. And the fourth one, this one concerns me, so I will define it. So, all right. So let's look at the first area that this connection comes up. So in approximation algorithms, so the equivalence that I care about is, so the algorithmic question is like, I want to say that some linear program, you don't need to know what linear program I write, but it gives C approximation algorithm for independent set approximation, if and only if some Ramsey number is bounded. So I will define this precisely what I mean. So let me first, so this Ramsey number is the notion of extremal question that I care about. The left-hand side is the algorithmic question. Okay, so just, I think most of you know Ramsey number, but just in case. So this, I often give this one to the high school students. So every 6 vertex graph has a stable set or a clique of size 3. Yeah, so this is like if you invite 6 people to the party, there is a group of 3 that know each other, or a group of 3 that don't know each other. So that's the kind of this is the classical Ramsey question. Basically, the goal is to show that there is either a large independent set or a large clique. So in a graph, and we can define Ramsey number here, RST. So S is the size of independent set. T is the size of clique. The question asks, how many vertices do you need? What is the minimum number of vertices such that your graph doesn't matter how the edges are arranged appear? How many vertices do you need such that it contains a stable set of size S or a clique of size T? Yeah. So in this language, it means that Ramsey number of 3 and 3 is at most 6. So when you have 6 vertices, you either you have independent set of size 3 or a clique of size 3. Is it clear? Okay. Yeah. So yeah, that's the Ramsey number. And so what is the known equivalence to computer science question to approximating maximum independent set? So basically, this is the classical one. It has nothing to do with approximation. The Ramsey type question is the following. Any n-node graph in the family of graph that I care about, it needs to satisfy some nice property that I'm not going to define. And if the graph doesn't have Q plus 1 clique, then the graph must have n over Q independent set. So if you don't have a large clique, you have a large independent set. So if you can prove this for some parameter, for all the parameter Q, then the algorithm that I don't define is going to give an optimal size of maximum stable set. So the algorithm will solve the stable set exactly if the Ramsey number holds. So this is if and only if. So it means that if you can prove this result, it gives this. Or if you can analyze the algorithm, it gives the Ramsey bound. So, okay. So it's not just one direction, it's vice versa. All right. So this is in the exact world where you care about knowing the optimal size of the independent set. So basically, you can view it in 2 ways. Like this is the algorithmic view of the Ramsey number, or the Ramsey number is the extremal view of this algorithm. So, okay. So that was implicit in the proof of in the original proof of Loas. And then if you look at the proof carefully, you will notice that actually it holds its scale with approximation factor. So if you can prove that the Ramsey number is at most S times T minus 1 times C, where C is some constant. Yeah, even super constant will still hold, but let's ignore that. Let's assume C is a constant. Then what happened is that it corresponds to, it will give you the result that the algorithm will give C approximation for maximum stable set and vice versa. So, okay.
Is it the same family F as on the previous slide?
Right, the family F needs to satisfy some property. It just needs to be closed under clique replacement. So but I don't, yeah. So we don't need to care about that. So usually, which is true for geometric intersection graphs or like several other graphs that I care about. So, okay. And let's say now, if you care about weighted version of a stable set, like each vertex has weights. And now the goal is to pick the set that has maximum weight, independent set that has maximum weight. There is also the extremal view of this question. So you can get C approximation for this algorithm, if and only if the fractional chromatic number is at most C times Q, if Q is the clique. So this is again if and only if. Okay, so that's the equivalence. So there are 2 equivalents. One is the maximum stable set, the cardinality. It's equivalent to the Ramsey number, and the weighted stable set is equivalent to fractional chromatic number. Okay. notice that one implies the other. So like the fractional chromatic number upper bound implies the Ramsey upper bound. So okay. So if you don't want to think about fractional, you can ignore it, but it's the converse will not be true. Yeah. Okay. So all right. So let's look at some examples. This is also a geometric intersection graph. If you have an interval graphs where the intersection between intervals define the graphs, then in this case, the clique is 3. One can always show that it's 3 tolerable. So this is also one of the exercise in undergrad courses. And that if you have clique of size Q, maximum clique is Q, then the graph must be Q colorable. And this implies that my linear program, the linear program algorithms, it will give exact value for maximum rate stable set. Okay. Basically, the proof that the proof of the extremal bound implies immediately the algorithm for computing maximum rate stable set. Okay, so how does the connection work? So I think this is too hand-wavy, but so I will just skip it. So I forgot to remove these slides all the time. So okay, so right. I would be happy to explain offline if you are interested in the connection. Okay, so let me try to tell you about how this connection arises in my work and how it gives me insight to tackle problems in the past. So this is more like a story. So recall that we have this connection. Okay, so now let's look at the concrete question, which was an open problem. So we are interested in computing stable set for the rectangle intersection graphs. So in this language, you are given rectangles and you want to find maximum collection that do not overlap. So
these are axis parallel rectangles.
Yes, right. Axis parallel. Yes, that's important. Yeah, thank you. Yes. So even this thing is NP-hard, even when all rectangles are unit squares, they are already NP-hard. And prior to my work, there have been several log-n approximations. And so algorithmic development, so that was my first PhD paper. So like long time back. So it gave log-n approximation, which improved the log-n approximation from 80s. So recently, it was known to be improved to constant approximation, and most recently to approximation. Okay, and so on. So one interesting consequence of my earlier work is that since due to the connection, the extremal connection, the connection between extremal combinatorics and the algorithms. So this algorithm is based on linear program. So it means that it directly upper bound the Ramsey number this way. So the Ramsey number of ST is at most ST log T. So in this graph class, I should mention that the trivial bound of the trivial upper bound is ST squared. So it improved from ST squared to ST log T. Okay. So yeah, so and you can use the connection as a black box. All right. So back then we did not know about extremal implication. So that's we did not state it in the paper. Okay. So one thing that I find is interesting is that the techniques from approximation algorithms community can actually be used to prove extremal combinatorics bounds. If we don't work on the approximation question, I don't know how to prove this bound. So I think this is something that is I think I find interesting in retrospect. So, okay. Let's look at another like a harder. Let's make the problem harder by putting weights on rectangles. In this case, the same. There have been similar development. There were log n approximation and log n over log n and quasi polynomial time approximation scheme. And also recently we can get log n approximation from for this problem. But this time we did it the other way around. So we proved the extremal result, and the extremal result implies log n approximation. Okay. So
Do you believe a constant approximation?
I think so. I think so. Constant approximation, yes. But I believe less the Ramsey bound that this log omega can be removed. I'm not so sure about that. So, but the constant by some other techniques, yes, I do. So, okay. So yeah, so this result improved the previous result from 1960. Okay. All right. So now so this is how it happens, the interaction between the two areas, it leads to this development. And so I want to raise some open questions that I tried for a while, but I don't know how to do it the right way. So usually we know the class called perfect graphs. So this is the class of graphs, the largest class of graphs where we know that this chromatic number and clique problem can be solved efficiently in polynomial time. And perfect graphs look like this. So there are so many graph classes inside perfect graphs. I don't even know some of them. Actually, I probably don't know many of them. So, okay, but let's forget about that.
Now, sorry, and the exact value here is the value. What parameter was it again?
Like the graph where the LP gives the optimal solution.
An LP4.
The LP that I mentioned before. Or like you can say that equivalently, you can say that perfect graph is the graphs where Ramsey number is at most s times t minus 1. So yeah, so this is the extremal definition. And yeah. So there are several definitions of perfect graphs. You can define it by, so this is the polyhedron perspective. Okay. So now, let's say I'm interested in solving stable set beyond perfect graphs. And I define somehow the almost perfect graphs to be the graphs where the LP gives constant approximation. Or like, you can also make the constant too. So then how do we characterize such a graph? I have no idea. So yeah, it's something I thought about for a while, but yeah, on and off.
Sorry, I got a bit confused. I'm sorry. Isn't it for perfect graphs you need SDP for the
yeah, you have to use SDP, but you can also define some clique constraint polyhedron, and the SDP actually gives the solution it optimizes inside that polyhedron. Yes, but yeah, it uses SDP for efficient algorithm. Yes. Okay. So, all right. So that will be the end of the first part. Yeah. So, and the second part, if you have been sleeping, you can now you can everything will be kind of reset. So, okay. So So the second part is about data structures. Again, I will connect some data structure question to combinatorics through my work. So now let me start with the extremal question that I care about. It's called forbidden matrix theory. So you have two matrices, and I say that, so these are 0, 1 matrices, and I'm too lazy to write 0 and 1, so I will just put 1. So 1 will correspond to dots, and whenever 0 exists, I will just leave it empty. Yeah, so dot is the ones. And then I say that one matrix contains another if the location of ones are relatively, it appear in the same relative sequences, the orders. Or the formal definition is that M contains P if you can remove rows, columns of M or turning 1 to 0, and in the end you get P from it. Okay, so that's the formal definition. But if you look at this picture, it will be obvious. So in this way, this matrix contains this pattern and this pattern because they appear in exactly this order. But it does not avoid this. It does not contain this pattern. So when it does not contain a pattern, I say that it avoids the pattern. Okay, so definition is clear. So in matrices, notice that you can have up to n square ones. And in this line of theories, we are interested in this bound. So it's another extremal bound. We are interested in the maximum number of points or the number of ones that you can have in a matrix that avoid P. So I give you I tell you the structure that this matrix avoids some pattern. And I ask you how many ones you can have if you avoid the pattern. Okay, of course it will depend on the pattern, but you can expect it to be much lower than, most of the time you can expect it to be much lower than n squared. So let's do some simple exercise to understand this definition better. Let's say I have an 8 by 8 matrix. It's like a chessboard. And now my forbidden structure is this one. Now you want to place the coins. The question is, how many coins can you place without violating this condition? So you want to place coins like this. Yeah, I put like this. So once I put the coins like this, I cannot put the coin here like this. If I put it here, then I would have this pattern. So if I don't want to have this pattern, I have to put the coins to avoid it. So, sorry?
2n minus 1, right?
Yeah, 2n, yeah, 15, yes, in this case, yeah. In this case, it's 15. So you can do it like this, or you can go this way. Yeah, it will be 15. And notice that you cannot do more than 15. One of the ways to see is that each diagonal can have only one coin, and the chessboard has 15 diagonals. So basically, you cannot put more than 15. And in this way, you can show that extremal bound of this n and this pattern is 2n minus 1. Okay, so I hope this exercise helps in understanding the bound, the definition. Any questions so far? All right. Okay, so now this is much harder. So how would you guess the asymptotic order of this one? So which one is the highest and which one is the lowest? So if I tell you that I don't have this pattern, or this pattern, or this pattern, which one would make my extremal bound go the lowest? First, second, or third? Okay.
The
The third?
first one. Oh,
Okay. So, all right. Yeah. So that yes. Let me give you the answer. So, the first one is n to the 1.5. The second one is n log n. The third one is n alpha n. So n alpha is the inverse Ackermann function. Is super low. So and I think the constant in front of it is simple. It's not quite simple. Yeah. Okay. All right. So actually, yeah, but basically each of these number, it has some computer science meaning. Like the first one is kind of the type example for force spanner. And the second one is if you use path compression without some heuristic, then you get n log n. And the third one also has computer science meaning. So each of the pattern here that I give is not arbitrary. It's I took it from something that has computer science meaning. Okay, so now let me try to define the problems that I work on. So I'm interested in sorting. So again, it's just you are given some numbers, the sequence, and so we all learn in basic algorithm class that you can sort in n log n. And this is tight. But then the question that is quite interesting, but it's still open, is that like what kind of sequence can we sort in linear time? Yeah, so if your sequence has some structure, we expect that some standard sorting algorithm should be able to sort it much faster. So do we understand this thing? So let me give you some example. In this case, let's say if your set is in this form, that if your sequence come from, so it's called sorting x plus y. So the input sequence always come from the sum of the two sets of the same size. Then in this case, notice that x plus y can have the size of n squared. And do we need n squared log n to sort it? So it's not clear. And the old result of Lambert shows that actually in this case you don't need log n. You can sort in linear time on the input size. So okay. So that's good. And in fact, if you only care about outputting a decision tree, you can have a decision tree of depth n log square n. So the comparison part is only you can make only n log square n comparison to reach the answer. yeah, of course, this is not enough to write down the permutation up to write down the output, but here we only have 3 there. So okay, sorry, I see. Okay. So yeah, so now that was the example, and let's see. So now the question that I care about is this question. If I'm given a sequence S, and this is the input permutation that I want to sort, and I know that S avoids some pattern of size K. So this is the structure that I care about. The structure is that it forbids some pattern of small size. Then can we sort this in linear time using linear number of comparisons? And yeah, so in the old days, so this question went back to Knut in 73, and so the question was, yes, when K equals to 3, basically if you avoid some size 3 pattern, you can sort in linear time. So that was long before, and I think until 10 years ago, it was open for K equals to 4. I think it was just resolved recently, so it's not even 10 years. So it was open for K equals to 4. All right, it was resolved, but I was not the one who resolved it. That's what I mean. So I want to. Okay, so what does it mean for a sequence to avoid the pattern? It's just that you encode the sequence as a matrix like this. The first number appears in the first row. So the columns corresponds to the numbers in the sequence, and the rows correspond to the location. So 1 appears at the first location, and 4 appears at the second location, and 5 and 3 and 2. So now you can talk about a sequence avoiding a pattern using the matrix definition as well. Okay, so this is the matrix representation of the input sequence. Okay, good. All right, so this question actually, if one notice carefully, you can phrase it in 3 questions. You can phrase it as 3 families of questions with different difficulties. So the lowest one here, you can ask it as a purely information theoretic question. You can ask how many comparisons do you need to sort such a sequence, but you don't care about the algorithm being polynomial time or something. So that was the lowest level. And if you make the problem a bit harder, you can say that you want polynomial time algorithm, but and also less number of comparisons. And you can also go further that, let's say I fix some algorithm that doesn't know the pattern that I avoid. For instance, imagine the sorting standard library that people distribute. Yeah. So in that case, you cannot say that, oh, I will encode this pattern into the sorting algorithm. So you have to use it as a black box. So in this case, this is, so I call it like the obvious algorithmic question. Okay, so we can ask it in 3 different levels of difficulties. And it turns out that the easiest question, it was answered a long time ago by Friedman in 1970s. So if you know that the input is drawn from some set A, the permutation is drawn from some set, then you can sort using log of A comparisons. So that's, and this is tight. So if I look at, so what I care about is the sequence that avoids some pattern P. Then basically the input that I have is the set of permutations that avoid P. Okay. So then the Friedman bound will say that, so I call this information theory bound. So if you say that the information theory bound is equal to this log of the number of permutations that avoid P. Okay, so that's a permutation avoiding P. And then in this case, it means that I can sort using also log of pi NP comparisons. But then for the upper bound on the algorithm, I don't know anything. And here is the part where it connects to extremal combinatorics. So if you look at the progress on the extremal combinatorics side, this counting the number of pattern avoiding permutation has been one sub area of extremal combinatorics, and most recent development, one of the most interesting development was the theorem of Marcus and Kardosh that shows that this log is actually linear. So, and the best known bound here is from Jacob Fox from 13. So now we know that this information theory bound is at most nk and at least n square root k. So this is the complexity of sorting that we know when the input avoids pattern of size k. So, but as I said, this one does not give efficient algorithm. It just upper bound the number of comparisons. All right, so now I will connect it to efficient algorithms. So one way to sort is to use oblivious approach by just insert the sequence into a binary search tree. And then you wait for the insertion to be done, and then you read the result out. Then you immediately get the sorted sequence. So that's what we do in like a first year undergrad course. And one question that is open, and I find it quite interesting, is that whether sorting in this way can achieve the best performance. And this needs some careful formulation of question, because if you don't formulate it in the right way, the clear answer is no. So the class of permutation that I care about should be rich enough. Okay, so now here is the result. It's one of my results with co-authors. So we show that actually there is a binary search tree algorithm that sorts in this type. So the upper bound of sorting is given in terms of extremal bound of another matrix. So the MP here is the input matrix. The P is the pattern that I avoid, and MP is the matrix representation. And the cost of the algorithm is upper bound in terms of the extremal bound of the tensor between this matrix and the other one. So, okay. So we lose a little, so the matrix become a bit bigger. So if you go back to this picture, notice that sorting requires this times EX and P. And now this result will say that sorting will take at most this another extremal bound, where this matrix becomes bigger, the pattern becomes a bit bigger. Okay. So, and this result implies immediately that if you tensor the permutation matrix with this kind of matrix, is called a light matrix. It has only one entry per column, so it's called a column light matrix. Then the number of ones here, the extremal bound is at most this thing. It's n times 2 to the alpha to the k. It's almost linear, but it has some alpha terms. And k is in the exponent of alpha. Okay, so that's the upper bound from this result.
Alpha is still the inverse Ackermann.
Inverse Ackermann function, yeah. So this is still like much better than log 10 times. So yeah. All right. So of course, So we have this reduction. It has some unnecessary tensor thing here, and the question is whether this is necessary. Is this I don't know. Okay. And in a more recent result last year, we analyzed this bound by not using the known result as a black box. So we use the structure of tensor matrix, and we chose that actually this bound is not k does not need to be the exponent of alpha. So you can pull it down here. So okay. And one interesting thing that I find in this work is that I think usually if you look from extremal perspective, nobody would want to analyze this matrix or this bound. It has no meaning. But then from computer science perspective, it matters. So it gives the upper bound on sorting. So basically, this is also one interesting thing that an extremal question that arises from CS application, it can be interesting on its own. Okay. So, and this is tight, unfortunately. So we need the alpha has to be there. So it ends this line of work, but not the sorting. So there was a follow-up work also recently last year. Basically, Opler gave the efficient data structure that matched the information theory bound for this question. But it's not the oblivious BST approach. It's not the binary search tree approach, and I don't think it's oblivious in the strong sense. And it is known that binary search tree also has some chance to do well. Okay, so this is the state of the art. So basically, the information theory bound is between nk and n squared root k, and there is an efficient sorting that reaches the same bound. But if you use oblivious approach, we are not quite there yet. Okay, so I want to conclude this talk. So I show you some connections that arise in my work that connect extremal combinatorics and computational questions in optimization and data structures. So they use different extremal questions. And the benefit is clear that you can transfer the techniques between the two areas, and it helps in making progress. Okay, thank you.
Any questions? Anyone? So somehow this way of defining sequences by fitting patterns is very natural. One thing which I didn't quite get is whether this is the only approach to the initial question which you asked, which is when does sorting can be done in linear time. So are there other interesting examples where it can be done and doesn't fit this paradigm?
Right. For instance, the x plus y sorting, it doesn't fit this paradigm. There are some others, but yeah, I think that it has nothing to do with answering that original question. Yeah, it's just like a sub question of that question. So
still interesting, of course. But thank you. Do we have any questions or reasons online?
Back in the definition of the F class, does it depend? Is it supposed to be for all Q? Or so this is a question from the beginning of the talk.
Yeah.
When you were defining the class F of graphs, which got work. Was it for all Q, or was it for if it was for particular Q?
So the graph class should be, so the proof that I use, it requires the graph class to be closed under click replacement. So if I have a vertex, let's say,
I think the question was about the quantification over Q.
Yes.
Right. Yeah. Right. So, but the Q is about proving the upper bound, right? Proving the extremal bound. So
no, I was just in the definition of the class.
Yes.
Where does the Q stand for? Because it wasn't in the other.
Right. So the question, right. So the extremal question that I asked, it has to hold for all Q.
Overall, that's what.
Yes,
that's what
yes. So you need to prove that for all Q, you can
Okay.
upper bound this. Yes.
Any other questions? No? All right, well, let's end the speaker again, and all the speakers of the day.